In video 4, we're going to graph a quadratic function by putting it into vertex form. Vertex form of a quadratic function, so here's a quadratic function, is the form that gives the function in a form that allows you to identify the transformations of the toolbox function. The toolbox function was x squared. So the vertex form is a form that allows you to see the transformations that were applied to the toolbox function to create the quadratic function f of x. So when we put it in this form, the vertex is actually located at, the vertex of the function is actually located at hk, at the ordered pair hk. So for example, if I put some concrete numbers in here, minus, let's say minus 2 plus 3, what I would want to identify is that the toolbox function, the squaring function, has a vertex that's located at 0, 0, and this allows us to see how the original vertex 0, 0 got moved. So from our work with toolbox functions, we would say, hey, I'm subtracting 2 from the input variable x, which means my graph has been moved 2 to the right. So if you move the input variable 0, 2 to the right, you'll get a positive 2 as your new origin location. Move it 2 to the right. And then the plus 3 says take that point and move it up 3 units, and it winds up at the point 2, 3. So what you can see is that you can identify the location of the vertex just by looking at the right or the horizontal shift and the vertical shift that get applied to the origin. If instead I had a function, say, that looked like x minus negative 3 plus 5, for example, then I would say, hey, the vertex for this guy is located at negative 3, 5. And if I combine this double negation, I recognize that I could rewrite this as x plus 3 plus 5. And so this plus 3, this 3 being added to the input variable, would take our origin and move it 3 to the left. And the plus 5 would move that point up 5 units. To the new point, negative 3, negative 3, comma 5. So essentially, when we put a quadratic function into vertex form, we're just putting it into a form that allows us to immediately identify the functional transformations that have been applied to the toolbox function x squared. So we're going to go through an example where we put a function f of x into vertex form, and I'm going to do it 2 different ways. So I don't have any graphing paper on this slide because I'm going to go through one technique of putting our function f of x into vertex form, and on the next slide I'll use a slightly different technique, and then I'll graph the function. To put a quadratic function into vertex form, we really just need to complete the square on the function, and there are 2 ways that a person can choose to put a quadratic into vertex form. So the first way, I'm going to go ahead and rewrite my quadratic function that I'm working with, and then I'm going to remember that in order to complete the square, I need a leading coefficient of 1 on my x squared term. So I'm going to go ahead and multiply both sides of this function by a half. So on the next line, I'm going to have half of an f of x sitting here, and then I'm going to distribute the 1/2 into the parentheses. So I'm going to get a half of 2x squared. A half of 2 is 1, so I get my 1x squared that I need. A half of 8 is 4, so I get 4x, and a half of 3 is just 3 halves. And then to complete the square, we know that we only work with the x terms, so I'm going to go ahead and subtract this 3 halves from both sides to get it out of my hair so that it's not in my way. So I'm subtracting 3x from both sides, and that's going to leave me with an x squared plus 4x, my 2x terms on the right hand side. And I'm going to grab the coefficient on the linear term. I'm going to grab that 4 and have it. And after we have it, we have to square it. So that's going to give us a 2 being squared, which is 4. So to complete the square, we add that 4 to both sides. And we completed the square. So now we ask the question, what was the square that we completed? Well, it's going to be x. And then I have a plus 2 that got squared, so it's going to be x plus 2 is the square that got completed. And this is a half of an f of x minus a 3 halves. I'm adding 4, so I need a common denominator for the 4. So 4 is going to become 8 over 2, which is still 4. And this is going to equal an x plus 2 being squared. And I get a half of an f of x. And minus 3 plus 8 is plus 5 halves. And now what we're going to do is kind of work backwards or rewind to re-isolate the f of x that was isolated to begin with. So I'm going to subtract this 5 halves right here from both sides. So I'll give myself a little line. So I'm going to have half of f of x equals, I'm subtracting the 5 halves from both sides, so I get x plus 2 squared minus 5 halves. And now to get f of x by itself, I need to multiply by 2. 2 times a half is 1. That's going to give me 1 f of x sitting here. But I need to multiply both sides by that 2. So times 2. Now distribute the 2 into the parentheses. So I'm going to have 2 times the x plus 2 being squared minus 5. And then I can read from this directly the location of the vertex. So the vertex, which is usually the origin, right? The vertex is usually the origin, but the origin gets moved via function transformations. It gets moved, I have a plus 2, so it got moved 2 to the left and down 5. I could take this one more step if I wanted to. I could rewrite this as x minus a negative 2 squared minus 5, because the vertex form technically has a minus sign right here. But if you're just trying to locate the vertex, you can stop when it's at the plus, because you can tell from that how the horizontal, how the function's been moved horizontally. So there's the vertex. I'm going to look at one other way of completing the square on a function, and then we'll go ahead and graph the function using that work. So another technique for completing the square that probably is a little bit simpler to use, but you have to be careful when you do it, is to recognize that to complete the square you only need the x terms, but you do need a leading coefficient of 1 on the x squared. So start by factoring the 2 off of just the x terms. So plus 4x, and if you do it right, you can distribute the 2 back in to check your work. 2 times x squared is 2x squared. 2 times 4x is 8x. And then plus, leave yourself some space. You're going to need some space right here, and then put your plus 3. So we didn't factor the 2 off of the 3, we just left them alone. And then you complete the square on the stuff inside the parentheses. So you find the coefficient on the linear term, which is a 4. You take half of the 4 and you square it, which means you're squaring a 2, which gives you a 4. Add that 4 inside the parentheses to complete the square. And then you want to look at the coefficient out here and say, how much did I really add? Well, I didn't add 4. I actually added 2 times 4 is 8 to the function. So to make it so that I've added 0, I'm going to subtract 8 off the outside. So again, 2 times 4 is plus 8, and out here I have a minus 8, and when I combine plus 8 minus 8, that equals 0. So I've essentially added nothing to the function by doing this. And now you go ahead and complete the square. You say, hey, I added the 4 to complete the square. Whose square did I complete? Well, I squared a positive 2. And plus 3 minus 8 is going to be minus 5. So if we look back to the previous slide, we'll see that we have exactly the same thing that we got right here. And we have fewer steps by doing it this way. The rub is that when we add the 4, it's easy to forget that we need to multiply that 4 by this 2 to figure out how much we really added. That's where you can run into trouble. A lot of times a person will add 4 and then they'll subtract 4 instead of 8 because they forget to multiply the 4 times the 2. And then from this we can see directly what the vertex is. The vertex is the point, hey, the origin, 0, 0 has been moved. This is a plus 2, so it got moved 2 to the left. And minus 5 moved it down 5. So the vertex is at negative 2, negative 5. There's the vertex on the function, negative 2, negative 5. In fact, if we think about the toolbox function is the function x squared, or the squaring function. It has lattice points here, here, and here. Those were the lattice points that we used for the toolbox function. So we can actually apply our function transformations to those key points just like we did when we worked with toolbox functions. So I can say, what are the transformations? It's move 2 to the left, multiply by 2, and then shift everything down 5. So I'm going to take this point, I'm going to move it 2 to the left, multiply by 2, so I double its height. It's a stretch, a vertical stretch, and then down 1, 2, 3, 4, 5. And I could take this point and do the same thing. A movement 2 to the left, multiply by 2, so double the heights, and then move down 1, 2, 3, 4, 5. So there I just moved or transformed my toolbox function points into the new locations. And it's nice to get one more point. I'm going to take the original function, f of x equals 2x squared plus 8x plus 3. And I'm going to get the vertical intercept by plugging in x equals 0, because x is always equal to 0 when we cross the y-axis or the f of x axis. So if we plug in 0, everywhere we see an x, this is just going to simplify to 0 plus 3, which equals 3. In fact, we can always just grab the constant term and say, hey, that's going to be the location of the vertical intercept. So we have a vertical intercept at input 0, output 3. And then we want to recognize that the vertex is located on the line of symmetry. So the line of symmetry is right here. So this point can be reflected in the line of symmetry over to grab one more point on the graph. And this is going to be the point negative 4, 3. And now we can go ahead and use those points to try to draw the parabola. And this is a long, stretchy one, so I know that I'm going to struggle with drawing it. And that's just a fact of life. It's coming up through from the origin through that point, and then it's got to pass through the vertical intercept, and then I have to draw down through this point, picking up that guy, and that's as good as I'm going to make my drawing.